Today we're having a talk from Stefanos Kourtis from the University of Sherbrooke in Canada. So he will be talking about physics-derived quantum algorithms for optimization, enumeration, and machine learning. Welcome, Stefanos, to ELAIS 2024, and I would like to hand over for you to take over the session.
Hello, and thank you for this opportunity to take part in this important program. Apologies for being a couple minutes late. So it's a pleasure to be with you today and to talk to you about this topic. I will share my screen now, which has to do with physics-inspired or physics-derived algorithms for various problems, and I will talk about a couple of those in this presentation today. Okay, can you see my slides?
Yes, please.
Great. All right, so let's get started. Here's an outline of what I will be presenting today. It has to do with the type of quantum resources we require to perform certain computations, right? So when we cast computational problems into the language of quantum computing, we require certain resources that are specific to quantum, to the quantum domain, for us to do these quantum computations successfully. And so I want to pose the question, okay, what are the resources necessary? And furthermore, when is it that these resources actually yield a process, a computing process that truly is beyond what we can do on a classical computer? And so to probe this question and to examine it from various perspectives, one way to proceed is to see to which extent we can use restricted models of quantum computations to solve a given problem. Because if we look at restricted models of quantum computation that can potentially be simulated on a classical computer, that gives us a flavor of how quantum computing would work for this problem, and it also gives us a benchmark that a quantum computer needs to go beyond, that needs to beat for it to be useful, right? To be actually useful, in the sense that the quantum computer actually does something more than what I can do on my classical computer, okay? And so the reason for posing this question is that in the near to mid-term, we don't have access to all the theoretical guarantees that quantum computing offers. Meaning, if we look at an algorithm like Shor's algorithm or Grover's algorithm, to operationalize these algorithms, to actually make them work on practical cases, we would need, first of all, large numbers of qubits that will have, each of which will decohere. And then when you have a large number of decohering objects, then very quickly you get just noise as the output. So we would need many of those decohering qubits, and potentially also we would need to error correct and make the computations fault tolerant, right? So this is very far away in the future. And so is there anything that we can do before we get to that point where we can use these theoretical guarantees of these algorithms? So if we talk about algorithms without these guarantees, we talk about near-term intermediate scale quantum devices, or NISQ devices, and this is what motivates this talk, is basically, can these devices give us anything useful, and how will we know that they actually perform something, some computation or some process, some protocol that is non-trivial. So I'm going to talk about two different restricted models of quantum computation. One is the Clifford model. And with this model, I'm going to address combinatorial optimization, which is a very, very broad class of problems and very, very ubiquitous in science and in technology. So I'm going to explain a bit how the quantum approximate optimization algorithm works, and then it's how it arises, and then its limitations, and how addressing its limitations leads to adaptive schemes, adaptive quantum circuits, and then I will show how these adaptive circuits can be in turn cast as Clifford circuits in certain cases. And next, I will talk about fermionic machine learning, where we talk about the restricted model of fermionic quantum computation and how we can apply that to quantum machine learning, specifically machine learning with quantum kernels or quantum kernel learning. And I will show you some benchmarks of this protocol applied to a couple of data sets. So with these two examples, I'm going to talk about optimization and learning. The thing to note is that both these techniques, both these restricted models of quantum computation have their fundamental basis in physics. And so I'll show you these examples, and then I will conclude, and we can discuss. Then, and also feel free to ask questions at any point in the talk. Okay, so that's the plan. So let's get started with some motivation. So quantum and hybrid quantum classical algorithms with noisy qubits use the same resources that theoretical or fault-tolerant quantum computers also use to solve problems. And these resources are always the following three: superposition, interference, and entanglement. Okay, so superposition means that we can put a qubit in a superposition of state 0, 1, and then we can do this for multiple qubits. Interference means that throughout the execution of our quantum algorithm, some amplitudes of our quantum states may be pronounced or diminished due to phase effects. So the phase of the wave function may interfere constructively or destructively. And so this is a resource used for quantum computation. And finally, entanglement, this correlation, this intrinsically quantum correlation between our components, our qubits. So, okay, if these are the resources, then how much of these resources are needed for solving a problem? How much superposition, how much interference, how much entanglement? And moreover, how much of these do I need my quantum computer to build in order for the classical simulation of the quantum computer to be difficult, right? Because if my quantum computer, when it runs a protocol or an algorithm, is easy to simulate classically, well, then I'm not gaining really anything. I could do the entire quantum computation, I could simulate it on my laptop or on a classical computer, right? So a quantum computer, to do something useful, should not be easy to simulate classically. And so we ask how much entanglement, for example, or superposition are needed for a quantum process to not be simulable classically. So this is an important question also for understanding what the limits are, or the boundary between classical and quantum computation. And so here I'm showing early work from Google, where it was purported that a quantum chip achieved some task. It doesn't really matter what the task is, at a level that was not reachable by classical algorithms. So to make this claim, you need to do two things. First, demonstrate that your quantum computer does something other than just produce noise at the output. And second, to show that whatever classical method I might choose to simulate what the quantum computer does, that method will fail. Okay, so at the moment of this proposal in 2019, Google purported that whatever they were doing on the quantum computer would take 10,000 years to simulate classically. But then actually, if you look at it carefully, you see that that's actually not the case. You can estimate that it would take like a couple months, say, on a big supercomputer at first, and then you think about it harder, and then you find that actually it would take a few seconds, and then in the end, you see that even on a relatively modest computing cluster, what they did was actually simulable. Okay, so this shows you. I'm showing this example to show you that, in fact, when somebody says that I did something with noisy qubits that cannot be done classically, whether that statement is true or not is actually, there's room for argumentation. And in fact, it has to do with whether this task can be simulated also on a classical computer. Specifically, what I wanted to talk about is whether we can emulate a task run on a quantum computer with a restricted model of quantum computation. And here I'm showing two such models. One is the Clifford circuits, and the other is the fermionic circuits. Both of these models of quantum computation, restricted models of quantum computation, are easy to simulate classically. Okay, so in the case of Clifford circuits, it means that I write a quantum circuit that uses gates that are in the Clifford group, and these gates are the ones shown here on the left. Importantly, the gates that are very common, namely the Pauli gates, also the Hadamard gate and the C0 gate and the swap gate, are all members of the Clifford group. So it means if I devise a quantum algorithm that uses this discrete set of gates, then this quantum algorithm can be simulated always efficiently on a classical computer. On the right, I have a different class of circuits that are built out of gates like the one shown here, with a certain number of constraints. So first of all, the gates need to look like the matrix that I'm showing here. It has this sort of block structure, and the blocks need to obey a determinant constraint that is shown also on the right. And furthermore, for this model, all of the qubits... Yes. Excuse me, is there... Is there a question? Sorry?
No, it was just a noise. It was a noise from background.
Okay, sorry. Yeah, so for the fermionic model, also one thing to keep in. So we have these constraints. First, the gates need to have this structure as shown in the matrix there. We have the determinant constraint also shown for the two blocks. And we also have a constraint that is all of our qubits need to be on a line. So we are not allowed to have longer range gates. This also means that we cannot have a swap gate. So we cannot really swap our qubits around. The gate set for fermionic circuits, on the other hand, is continuous. So meaning these A, B, C, D, and W, X, Y, Z, these entries of this unitary that represents our gate can take continuous complex values. Okay, as long as they fulfill the determinant constraint. Now, with these circuit classes, we can do quite a lot, actually. So, in fact, if we look at the resources that we started from, meaning superposition, interference, and entanglement, both these models can build arbitrarily large superpositions. So, if we have n qubits, a Clifford circuit can build states that contain 2 to the n non-zero amplitudes. And for fermionic circuits, it's a bit lower, but again, it's a very, very large superpositions. Both of these circuits contain elements that have phases or negative signs. So, for example, in the Clifford group, the S gate contains an imaginary unit, and the Z gate contains a -1. So it means that these add phases, and if they add phases, they can produce destructive or constructive interference. And similarly for the fermionic circuit, since these parameters A, B, C, D, etc., they are complex numbers, they can have arbitrary phases, and again, we can have constructive or destructive interference. And finally, entanglement. Since in the Clifford group we have the C0 or the controlled gates, this can build arbitrary degrees of entanglement. And similarly, because the gate that you see on the right for fermionic circuits is a 2-qubit gate, and it is entangling, at least for many choices of the parameters, also fermionic circuits can build a lot of entanglement. So here we have two restricted models of quantum computations that are classically simulable, but at the same time, they can build a lot of superposition, interference, and entanglement, okay? So this tells you that for quantum computing to be useful, it doesn't need just to build these resources, superposition, interference, entanglement, but it also needs to build them, to introduce them in very specific ways, okay? Very specific ways that cannot be simulated with these circuit classes. So instead of asking how much of these resources we need for a given computation to be quantum computation to be useful, we need to ask what kind of these resources is required for a useful quantum computation. But we may also ask the converse question, which is, okay, these restricted models of quantum circuits can be used to implement algorithms, right? And so if we implement algorithms with these classes, how do these algorithms perform? And crucially, how do they perform compared to general quantum computations, right? Or even classical computations? So this is the main motivating question for this talk. So, okay, let's take the first class of restricted quantum circuits, which are the Clifford circuits that we saw earlier. So here we will want to do a combinatorial optimization with a quantum computer. And so to do optimization, one of the earliest proposed protocols to do this is called quantum annealing. And in quantum annealing, what we do is we start from an easy to prepare known state, whose Hamiltonian, or rather, for which we have an operator that stabilizes that state. So basically, we start with an initial state and a Hamiltonian, or an operator, for which this state is an eigenstate. And then we also have another cost function, or Hamiltonian, at the end, which is the one to which we are seeking the minimum energy state, okay, or the actual maximum the configuration that actually optimizes that score, okay, or that cost. And so then what we can do is we can build a time-dependent cost function that starts at time t equals 0 from the easy to prepare Hamiltonian, which is this HB here. So at time t equals 0, we will have that Hamiltonian. And at time t equals capital T, we will have this HC, which is the problem Hamiltonian that whose solution we seek. So due to quantum mechanics and the adiabatic theorem, if we do this, if we prepare an initial eigenstate of HB and we vary, we let time, or we make this capital T very, very long, this duration of the total duration of the protocol very, very long, we are guaranteed that at the end of this protocol, we will obtain the ground state or the optimum for this cost function HC here. This is just by guaranteed by quantum mechanics and the adiabatic theorem, okay? On the other hand, this time capital T can be very, very long, okay? In fact, exponentially long, where exponentially means exponential in the number of variables involved in this problem. Okay, so this is the way a quantum annealer works. So for example, the quantum devices built by D-Wave, the company D-Wave, they actually try to do this, okay? But I may want to, say, simulate this on a quantum computer that only implements gates. So the way to implement this protocol on such a quantum computer, instead of imagining an evolution with this time-dependent Hamiltonian, I break it into pieces, smaller pieces, that then I alternate. So if I slice the time t into tiny time intervals delta t, I can decompose this evolution into two different evolutions with these parameters beta and gamma. And these parameters correspond to what I had in the original protocol. And there's some error that I can make small enough by picking this delta t to be small enough. And so then how do I go from delta t to t? Well, I stack this e to the minus I delta t ht many, many times, one after the other. So if I do that, I will have these two terms, e to the minus I beta hb, e to the minus I gamma hc, one after the other. So I'll have if we call this beta and this gamma, I'll have beta gamma, beta gamma, beta gamma, etc. Many, many times. So if I do this a very large number of times, this protocol is equivalent to the original protocol of quantum annealing. But if I do this only a few times, and instead of picking these specific values, beta and gamma, I let them free as parameters, then I obtain something called the quantum approximate optimization algorithm, or QAOA. So in short, instead of doing a very long sequence of these two operations, I will do a shorter sequence. And instead of picking the beta and gamma to fit the adiabatic protocol, I will just leave them as free parameters and try to optimize over them. Okay, so that's QAOA. So here is P-level QAOA, which is basically what I showed you before. Sorry, here the notation has changed. What I had as HB before is now HM. And basically you start with this initial easy to prepare state, and then you apply sequentially these two operators, and you do this p times. Okay, this produces a state that depends on these parameters beta L and gamma L for each layer or each level. And so then in the end, what I want to do is optimize this score, meaning reduce beta and gamma, or optimize beta and gamma such that I minimize this score. Okay. So this method, this algorithm QAOA, drew a lot of attention in recent years because it is easy to implement on near-term hardware that allows for quantum circuits with parameterized gates. So this means each gate in my circuit can have a parameter that I can tune. Okay, and the reason for that is that the optimization of these parameters can be done classically. So meaning I pick these parameters, beta and gamma, I pick a choice, and then I evaluate this on the quantum computer. Then I tune these parameters and evaluate this again. And if this this change reduces the score that I'm trying to minimize or maximize, then I keep changing the parameter. Otherwise, I do something else, right? I change a different parameter. So that's QAOA. The problem with QAOA is that it requires a lot of gates to implement these operations here, right? So because this these two Hamiltonians, HM and HC, HM is relatively easy to decompose, so that's not a problem. But applying this many times is an issue, and also it has an issue of convergence. Remember, we derived QAOA from the adiabatic quantum computation, where here we want to make delta t very small, and if we make delta t very small to implement this sort of protocol, we would have to repeat these two operations many times, whereas here we stop at p, and p is of order, I don't know, 5, 10, right? Whereas we would need to do it for p equals 1,000, say, to actually approximate the adiabatic algorithm. So to improve convergence, people came up with adaptive QAOA methods. And so in this case, instead of applying just the sequence here with a fixed operator HM, we actually pick a different HM for each layer from a pool of different possible operators that includes what we have in original QAOA, which is this sigma xi, but also includes other possible terms. And we pick these so as to maximize what we call an energy gradient, or basically we pick at each level of the algorithm, we pick the operator to put in our QAOA that maximizes the gradient. So it means it improves the score that I'm trying to optimize the most. And so then we pick that, and then we move on to the next layer, and then we also optimize these beta and gamma parameters as we go along. Okay, so so far we've covered what QAOA and adaptive QAOA are, and now let's try and apply it to a problem. So one thing that I should say here is that in these QAOA techniques, basically what we're doing is, especially in adaptive QAOA, we are looking in the space of circuits for the best circuit that solves our problem. Okay, so if I go back to QAOA here, we're, instead of looking through the space of solutions of our cost function, here HC, we are instead looking in the space of parameters, beta and gamma, that will actually give us a solution to this HC. And we vary those to get to a solution of our problem. Now in adaptive QAOA, on top of doing a variational search over parameters, we also do a search in the space of possible circuits, because now we are looking also through the various combinations of gates that we can apply in the circuit. Okay, so adaptive QAOA is a joint search in the space of parameters of the circuit and the gates applied. And so we might ask, okay, at the end, what kind of circuits do we find? Okay, what kind of circuits do we find for a given problem? So here I'm showing an application to a problem called maxcut that has this form. We have these Zi and J operators and some weights for each pair. This is defined on a graph. So you imagine a bunch of connections between nodes. And we want to optimize this score here. okay, using adaptive QAOA. And so here I'm plotting the values of the parameters we find for a 10-layer ADAPT-QAOA circuit. So what I want to show here is that basically all of the parameters take very specific values, or almost all of the parameters take very specific values in both. These are for two different instances of the problem. And so what we find is that for the Hamiltonian layer, for the cost layer, we always obtain more or less the same value. Here there's a single exception, and that value is 0. Okay, so it means that the Hamiltonian layer doesn't really matter. And the mixer layer, the parameters, they are either 0 or they concentrate around this specific value here, which happens to be -π². But for this mixer that we find here, for this, it's one of these operators here in this pole. Specifically, it's this YZ mixer. And for this parameter choice, π², the entire circuit becomes a Clifford circuit. So we get very close to a Clifford circuit. So what does this tell us? Remember, ADAPT-QAOA, as we discussed, searches through the space of all circuits and of all parameters. And what it finds is a Clifford circuit, right? So the optimal circuit to solve this problem that we want is a Clifford circuit. Okay, so then if it is a Clifford circuit, then let's reduce the algorithm to search only through the space of Clifford circuits. So this leads us to the first algorithm that I want to show you, which is the adaptive Clifford algorithm for combinatorial optimization. So now we go into this restricted class, the first one that we saw earlier, and we ask, how can this restricted class of quantum circuits be used to solve some combinatorial optimization problem? And so the high-level strategy here is we start with setting all of this should be gammas here. Basically, the cost layer of the algorithm is set to 0 because this is what ADAPT-QAOA tells us to do. Okay, this dashed line here is basically all zeros. And then the betas here, the parameters for the mixer layer, we discretize them so that all of the mixer layers are Clifford, but we search through all possible Clifford gates for this layer. And so we do this for each layer, again using a gradient criterion, and this gradient is also easy to simulate and to evaluate on a classical computer. And we see how this algorithm, and we repeat this for a certain number of layers and measure the output state. So how does this algorithm perform? Okay, now we have a classical algorithm or a restricted quantum circuit that is efficiently simulable on a classical computer, and we want to compare this with how this with say a classical algorithm, a native classical algorithm. And so here I'm showing results for a weighted max cut for a variety of different graphs. So here I have 3 regular graphs, 8 regular graphs, and random Erdos-Renyi graphs. And I'm comparing the performance of adaptive Clifford circuits with a classical algorithm that here is GW as a function of the number of vertices in the graph. And the score that I'm showing is the minimum energy, right? So the lower the energy, the better the algorithm. So what we find is, first of all, we can scale up to 1,000 vertices with ADAPT-Clifford. Okay, means 1,000 qubits. Okay, in general, we cannot simulate 1,000 qubits on a classical computer. Okay, but remember, this is a restricted class of circuits, so we can simulate as many qubits as we want virtually. And not only this, but if you compare the solutions found from using the two methods, actually the adaptive Clifford circuits outperform the classical algorithm in almost all cases. Now, this should be taken with a grain of salt. We're not saying that ADAPT-Clifford is a better algorithm overall, but basically what we want to show is that this restricted quantum circuit class that is efficiently simulable classically can solve the problem very efficiently. So in turn, what this means is that for a quantum computer to do better, to do something useful, it would need to do better than this, okay, better than this. So already I have a useful benchmark to compare my quantum computers against. Okay, so that's the story about the adaptive Clifford circuits and the quantum approximate optimization algorithm with a restricted class of Clifford circuits. The take-home message here is that here a restricted class of circuits performs very, very well, and it is an open question whether a quantum computer can outperform this performance. Okay. Now, let's turn to fermionic quantum computing and to machine learning. So there has been a lot of talk about quantum machine learning recently. So it's an explosion. It's an exciting field. It's an explosion of research in this field. But what is it about? So when people talk about quantum machine learning, they might talk about different things. The first thing, which is not what we're talking about here, is to use machine learning to improve quantum computing. This is not what we do. Instead, we go the other way around. We're talking about quantum computing applied to machine learning tasks. But there are several ways to go about it. The first one is to say, okay, here's a machine learning task. Here's the underlying computation that needs to be done. For example, matrix multiplications or decompositions, linear algebra in general. And we want to try and speed up these algorithmic primitives underneath machine learning using quantum computing. Okay, so this is what sometimes people call the first wave of quantum machine learning. The second option is to perform machine learning tasks on quantum states, right? So I have a quantum computer now. It can produce quantum states. Quantum states are hard to manipulate and to classify, say. So let's come up with techniques that can classify states that I build on a quantum computer. Okay, so sometimes this is called machine learning with quantum data. When people talk about quantum data, it means that they want to operate machine learning protocols on quantum states. And the third option is to use quantum computers to perform machine learning tasks on classical datasets, meaning datasets like the MNIST dataset or like any dataset that you might have sitting on your classical computer. Let's try to load it on a quantum computer and use the quantum computer to perform the machine learning task, hopefully with some performance benefit, right? Because otherwise there's no need to use a quantum computer. So here we're interested in the third case, quantum machine learning on classical data. Specifically, we will focus on one type of quantum machine learning that uses a kernel method. A kernel method is a very commonly used fundamental technique in classical machine learning that uses a so-called feature map to take data given in a space, in an input space, and promote them into a larger space in which I can classify data more easily. So a cartoon of this is shown here. So I have my data. These can be, say, pixel, this can be images, so like each point, so each point here will be an image, right? So it's a certain number of real numbers, each one representing a pixel. So now what I want to do is promote this data into a larger, and so, sorry, in the original space, you know, these data looks kind of chaotic, and there's no separation between different classes. Say red here represents one class and blue represents another class. And in the original space, if I just look at the data, the raw data itself, I can't make sense of which class is which. So the idea now is to promote this data into a much larger space. That's called the feature space, such that in this big space I can find a linear separator, such that, you know, see here, red squares are mostly on the right of the line and blue circles are mostly to the left of the line. And so there's a nice analogy between kernel methods and quantum computing, because in quantum computing we can take our original data, put them as parameters in a quantum circuit with parameterized gates, and promote our data to quantum states in the large Hilbert space. And hopefully in this large Hilbert space, now we can do a classification like in the kernel method case. So what a kernel is usually is the pairwise distances between points in this large feature space. And we know how to do this also in a quantum setting. One notion, for example, of distance is the fidelity between quantum states. So low fidelity means large distance and vice versa. So if I have this phi x, here I'm writing in terms of density matrices, I can test for similarities by testing for fidelity. And here I show a circuit for how to measure fidelity between two different quantum states are prepared with quantum circuits. And so I can build this kernel matrix. And now based on this kernel matrix, I can do classification with some tricks like a support vector machine. So the important thing is to just get this kernel matrix, okay? And the way to do this is with quantum circuits. So I have a quantum circuit that has parameters, and in these parameters, I can put in my data points like X and Z, right? So say I have a gate, like a rotation, a Z rotation with an angle theta. Now this theta I use as a parameter that will encode my data points. And so I do this for one data point, say here this U phi of X, and then I do the dagger for for Z, U phi dagger of Z. And with this circuit that starts in the all zero state and is measured at the output, I can actually evaluate this kernel, this inner product type of kernel. Okay, so the only thing I need to measure at the output is the probability of measuring the all zero state that I put in the beginning. And that will give me this as its expectation for these two data points. So I do this for all pairs of data points, and I obtain my kernel from the quantum machine. Okay, so now since we can do this, we can try and model this with just fermionic quantum gates, which is this type of gates that I showed you in the beginning. And there is a way to actually efficiently simulate this, and I will not go into detail, but for those of you who are in theoretical physics, you can simulate this with Majorana particles. It doesn't really matter, but what matters here is that here I have a gate with free parameters. I can parameterize it to encode my data and build a kernel like this using only fermionic gate circuits. And so here's, for example, a way to implement a feature map. Okay, here these Ry, theta L these theta L's are the parameters, and Ry are Y rotations. So this is a way to encode my data. And I also have entangling gates to actually build superpositions and entanglement and everything. So this will give me, I build a circuit out of these feature maps. Of course, I can make them bigger with more qubits, etc. And then I have my quantum kernel. And so here now I'm looking at certain data sets. Specifically, I'm looking at two different data sets. The right one is digits, and the left one is a database of medical imaging pictures. And so I compare now performance between fermionic quantum computing and the regular parameterized quantum circuits, meaning full quantum computing. And what I find is that in both cases, the performance of fermionic machine learning, here you can just follow, for example, the green stars in both cases. In this case, it's very close, with parameterized quantum circuits coming up on top, meaning showing better test accuracy. This is, by the way, as a function of the number of features that I use. Whereas in this case, again, they are comparable, but the fermionic machine learning actually performs better than a regular parameterized quantum circuit. Okay, so the morale of the story here is that, again, like in the previous case with the Clifford circuits, any useful truly quantum algorithm for machine learning would have to outperform the fermionic machine learning, because otherwise it is useless. Okay. Okay. So with this, I would like to conclude and take your questions.
Can I?
Yes.
Okay. Can I ask a question here on this slide? So, looking at the identification, the keys, we have parameterized quantum circuits, and then there's another one, fully parameterized quantum circuits.
Sorry, this is not fully. Sorry, it's not full. It's fermionic parameterized quantum circuits.
Okay.
Yeah. So parameterized quantum circuits is what you would call fully parameterized quantum circuit. This is like any gate. Basically, here we could put any quantum gate. Of course, we cannot simulate these blue. You see, this blue curve stops here because beyond this number of features, we cannot simulate on a classical computer anymore. And also, these experiments we could not really run on a quantum computer because of noise. Like we cannot get to this point, right? In contrast, all these other three, especially these two, FPQC and HFPQC, are the fermionic ones, which means we can simulate as many features as many qubits as we want. And so these are the two to be compared, basically blue with the triangles, or blue with green here. Okay, does this clarify?
Yes, it's clear now.
Yeah. Also, just to mention here, you need to pay attention that the y-axis is different. So here, all the accuracies are much higher than in this case. Okay, so what we saw is these two restricted classes of quantum circuits that we can use to express different quantum algorithms in this restricted setting. And because these circuits are restricted, we can actually do scalable benchmarking. So we can, go to large system sizes and look at how these algorithms perform, right? This gives us an idea of how quantum computing would perform in much larger scales than what is accessible with current quantum computers or with simulation of quantum computation on classical machines. And furthermore, these techniques give us a useful benchmark to benchmark actual near-term quantum computation, because any actual quantum computation would have to perform better than the restricted techniques for it to be useful. And then a final point to make here is that in some cases, it might be that these restricted circuits, using these restricted circuits, we can cook up a new classical algorithm, right? So it's derived from quantum circuits, but it runs on classical computers, and it can be competitive with other classical algorithms. So that's an interesting side effect that has come out of these studies. Okay, with this, I would like to thank my team and collaborators for these two different projects. If you would like to read more about these works, you can find the references here. And with that, I will take any more questions you have.
Okay, so when you said the benchmark to serve as a benchmark, so what you mean is that, let's say you develop your quantum algorithm and then you use it on a classical data, and you see the performance. After that, if you can encode the same data into the Fermi machine learning and get the performance, that's how it will help you know that. Or
Exactly.
Okay.
Exactly, right? So here, for example, fermionic machine learning for digits dataset with an increasing number of features has this test accuracy, okay? So for any quantum kernel method to actually be useful, it would need to beat this, because if you're not beating this, then it means I can do better with a restricted quantum circuit class, right? So that's the point. But on the flip side, what you can do is on your classical computer, you can investigate how the quantum resources actually enable you to do these computations, right? So you use the restricted class, you can now scale up to bigger data sets, like beyond digits. You can do MNIST, you can do fashion MNIST, etc. Because these classically simulable quantum algorithms are actually scalable. So you can also try and see which problems are better for a quantum computer potentially and which are not.
Okay. Lisa, also, if you can go back to this one. So the math case here, the fermionic circuits, I don't really get how it is constructed with this math case.
Yeah. So let me see. Maybe I can. Great. I can write. So if you imagine your qubit lines here, so a matchgate circuit needs to fulfill 3 conditions. The first is that your gates need to look like this, meaning these zeros here need to be zeros. Okay, this is called a parity constraint, and it doesn't. It doesn't really matter what it is, but these need to be 0. That's first constraint. Second constraint is that these 2 blocks, A, B, C, D, the outer block here and the inner block here, are shown here, and the determinants of these 2 blocks need to be equal. Second constraint. Third constraint is if your qubits are on a line, like I show here on the right, the gates can only touch neighboring qubits, like this. And never qubits across, they can never, go across 3 lines, okay? So these are the restrictions for how you can write circuits with only match gates and only planar circuits. So with these restrictions, if you write a circuit that fulfills these 3 conditions, then that circuit can be simulated classically.
Okay. Thank you very much.
Sure. Other questions?
Yeah, hello. I think I have a question.
Yeah,
Hello.
go ahead.
Does that mean that from the beginning, I heard you mention that the normal quantum circuits are not being able to take a large number of qubits, right?
Not for the moment, yeah. So we can't have large number of qubits because the machines don't exist yet. We have like maybe 50 to 100 qubits. And on the other hand, we can't simulate those classically either beyond, say, 50 qubits.
Okay. So in that case, meaning that the fermionic circuit is able to take much number of qubits compared to the normal quantum circuits.
Oh yeah. Yeah.
Okay.
Yeah. So for matchgate circuits here, I'm showing an example of like going here, you see up to 64 qubits without any problem, right? This we can scale much more, can go to thousands of qubits. And before, for the Clifford case here, you see I go to 1,000 qubits. In all cases, no problem. Okay. So this is not reachable with any existing quantum computer or with any simulation of a quantum computer.
All right. Thank you.
Okay. In the meantime, let me thank again the organizers of this very interesting program. It's been stimulating talking to the various trainees in my mini project, and thank you for the opportunity to talk to you today. Also,
you're welcome. Welcome. Also, thank you for honoring our invitation. We are grateful that you are able to make time for this program.
Great.
So,
and to the trainees who participate, those of you who are interested in participating in research or doing a degree at some point, and if you would like to consider Sherbrooke and Canada for your degrees, don't be a stranger. Keep in touch. We're always looking for talent.
Okay, thank you. I think you can then give the participant your email just in case they will need some answers to some of the questions, and also information about it.
If there's follow-up questions, you can contact me via email or so I can actually put that in the chat.
Okay.
Me make sure I include everyone. Yeah. Okay.
So thank you very much again. Nice meeting you.
Yes, thank you as well. Have a good day.
You too.
Bye.
Bye. Okay, so participants, we come to the end of today's program and hope to see you within the week. Yeah, Philip, do you have a question for me or for Stefano?
Please, is for you.
Oh, okay.
Okay, good evening. Please, the email concerning the attendance, the color code. Sorry, I missed the information it conveys. If you could please help us.
The current email or?
Yeah, you've sent us some emails concerning the attendance.
Yes.
Yes, there are some
it has
colors.
To do with those, wait, let me cross check. I think I wasn't around for that. But it has to do with those who are in good standing, those who are in the danger zone, and those who are in between. It's with respect to how consistent are you when you attend these meetings. It's at first we used it to give the mini projects. So now also use it for a different thing based on how consistent you are. So that is what it means.
Oh, okay.
Okay.
Please,
I hope.
Come.
Okay.
You go ahead, please.
Yeah, you can ask your question.
Okay. Please, I would humbly ask that then you maybe indicate it in the email. Maybe what red stands for, what yellow, and then I think green also. What they stand for, what they mean. Yes.
Okay. I was saying that the email, he has posted the email in the chat. So if you need to contact him with respect to any other questions, and as he said, he are looking for talent in the university. So you can also send some application or check the application of the applications on the site of the university and see whether you can apply to some of them. So we have come to the end of this meeting. If you don't have any other question, then we'll call it a day.